In our previous video, we explored the intuition behind why the biased sample variance equation tends to underestimate the population variance. In this video, we will delve into a mathematical derivation of the sample variance with a correction of using n-1 in the denominator. In our earlier demonstration, we established that the sample variance using n in the denominator is smaller than the sample variance using the population average, which in turn is a reliable estimate of the population variance. Now for the mathematical derivation, let's subtract the expected value of both terms and examine the outcome. Considering both equations where the denominator is n and the distinction lies in the utilization of the population and sample mean, we include both expressions within the expected value. Expanding the terms raised to the power of 2, we will move this up for more space. We rearrange the resulting expression. Notably, the cancellation of x sub I squared terms, allowing for further simplification. Several terms from the sum are extracted by multiplying them by n, and the n in the numerator is simplified with the n in the denominators. The last term, the average of sample, is replaced with x bar. Further expanding and rearranging the equation, we condense the terms into the difference of the sample and population average squared. The expected value presented aligns with the definition of the variance of the sample mean. By expanding the sample average, expressed as the sum of the samples divided by the total number of samples, and leveraging variance properties, we arrive at a new expression. We then replace the variance of the sample with sigma squared. We cancel an n from both the numerator and denominator. This leaves us with an expression for the variance of the population over the number of data points in the sample. Given that the sample variance using the population mean approximates the population variance, we make this substitution. We separate the terms, we group the population variance, and bring this to the top. The result is an expression for the population variance. Expanding the equation of the expected value of the biased sample variance, canceling the n from both the numerator and denominator, we arrive at the final expression. This correction factor is commonly known as Bessel's correction. In summary, we have provided empirical, intuitive, and mathematical derivations to explain the use of n-1 in the denominator of the sample variance to estimate the population variance. This correction applies to both the sample variance and the sample standard deviation. If you found this content valuable, feel free to subscribe to the channel.